Hello, my name is Ben Dribus. I'm a math professor at William Carey University in Hattiesburg, Mississippi, and a member of the Foundational Questions Institute. This is video number 2 in a series of short videos demonstrating advances in artificial intelligence I've been working on, involving novel artificial neural networks for use in science and medicine. The goal of these videos is to help establish collaborations and partnerships with others who are interested in developing or using this technology. You can find my contact information on each slide. In this video, I will carefully explain what I mean by novel artificial neural networks and how the sparse, local, highly connected architecture of these networks differs from that of most networks in use today. These are illustrations of structural components of hybrid networks. I'll demonstrate how these networks achieve both superior connectivity and local feature analysis. In the previous video, I demonstrated software I've written that allows hybrid network architecture to evolve naturally in response to the specific challenges of a particular data set. A brief recap of this will be helpful moving forward. The network I demonstrated is for breast cancer diagnosis. The nodes represent neurons and the edges represent synapses. The 30 input nodes receive 30 cellular measurement indicators for each patient, while the 2 output nodes provide the diagnosis of malignant or benign. I chose to train the network with 469 patients, then test its diagnostic accuracy with the remaining 100 patients. Initially, the network structure was too local and poorly connected. Using its freedom to self-modify, the network pruned and added edges during its training process, keeping the total number of edges constant for apples-to-apples comparisons. The connectivity improved to 100%, and the resulting network diagnosed more accurately than a conventionally trained network with the original structure. This provided an initial demonstration of novel, sparse, local connected network architecture. Now, since this video and the ones following it begin to involve some technical details, it's useful to establish conventions. Red text is for emphasis and blue is for math notation. Information flow is up the page, as in Minkowski's spacetime diagrams in physics. Networks may be represented either in detail or in schematic form. When in doubt, I try to over-explain rather than under-explain for the benefit of non-experts. References will be discussed comprehensively at the end of the video series. Here's a preliminary look at a novel network architecture, restricting attention to the family of nodes and edges terminating at a single output node. This is called the perceptive field, or the history of the output node. It has an interesting self-similar or fractal branching structure. The overall network has hundreds of times more edges than this. The network may be partitioned into layers, in this case just 5. Usually each layer has sublayers, but here I've just chosen one sublayer per layer, again for simplicity. The green input layer at the bottom receives the data to be analyzed, which represents the questions we are asking the network. The blue intermediate layers are called the deep layers, which is what puts the deep in deep learning. The deep layers perform most of the actual analysis or thinking in the network. The output layer is where we read off the results or answers given by the network. Now, so far this description could apply to almost any artificial neural network, but here we focus on novel hybrid networks with a combination of regular local connections between nearby nodes and sparse non-local connections, usually random, that reach far across the network. This hybrid combination produces the self-similar branching pattern in the perceptive field. The result is that each output node sees a family of overlapping patches of varying sizes in the input layer. We typically choose these patches to completely overlap so that the network will be highly connected. Here, for visual clarity, I've cut off the network before all the patches overlap. I'll animate the diagram so that you can see it from different angles. It has a distinctly biological look, like a clonal colony of trees. Now, as we just saw with our novel hybrid network architecture, 3 important ways of arranging network edges are local configurations, non-local configurations, usually random, and hybrid combinations of these. Here I illustrate the differences among these configurations. In a local configuration, each node is connected to a small patch of nearby nodes called a kernel. Typically, such a kernel has algebraic as well as geometric significance because the same weights are shared among corresponding kernels in different locations. Such weight sharing is useful for detecting local data features, as in the important case of convolutional neural networks, or CNNs. However, because edges don't spread out much in a local configuration, it's bad for overall network connectivity. An opposite type of configuration is a non-local configuration, usually random, in which connections are widely scattered. This is excellent for network connectivity, but bad for local feature analysis, because most of the local connections that could detect such features are absent. A third type of configuration is a novel hybrid configuration, in which a local kernel architecture coexists with sparsely scattered non-local connections. Hybrid structure can detect local features with its local edges, while simultaneously connecting the network thoroughly together with its non-local edges. Now, to adequately compare these structural alternatives, we need an appropriate definition of network connectivity. For a network like a social network where information flows in both directions, high connectivity simply means that there are sequences of edges connecting typical pairs of nodes. But for our networks, we need the connecting edges to line up correctly in the input to output direction, so that a typical input node actually transmits information to a typical output node. Together, two such nodes are called an input-output pair. We define network connectivity to be the percentage of input-output pairs that actually transmit information. We can also think of connectivity in terms of looking back in time from an output node along incoming edges and checking which input nodes it can see. These nodes and edges are called the perceptive field, or the history of the output node. For example, let's look at a totally local network with 3 layers of 100 nodes each. Here I show just the paths through the network that terminate at a given output node. Following these paths back in time, we can see that this output node is connected to 13 input nodes. This is its perceptive field in the input layer. Because the network is totally local, the perceptive field is relatively small and locally concentrated in this case. Output nodes near the edges of the network can see even less, because perceptive fields can only grow toward the interior of the network. Averaging over the entire output layer, the typical output node sees about 11% of the input nodes, so this is the network connectivity in this case. This means that the answer given by a typical output node is not influenced in any way by most of the inputs. So we infer that high connectivity is a necessary condition for good network performance, because outputs can't provide accurate answers about data they can't even see. The importance of network connectivity presents us with a dilemma. On the one hand, local networks tend to be poorly connected, while random networks are well connected. On the other hand, random networks lack local feature analysis capabilities. An obvious question is if we can construct hybrid networks with enough local structure to analyze local features and enough non-local structure to achieve adequate connectivity. For this purpose, we will examine a spectrum of networks with equivalent layers and edge numbers. The only differences among these networks will be the proportion of edges that are local versus random. This will provide apples-to-apples comparisons of connectivity. We begin with a totally local network with 5 layers of 100 nodes each and diamond-shaped kernels. The connectivity of this network is just 30%. We will construct a table with progressively more random architectures and examine how the connectivity changes. The endpoint will be a completely random network shown here, which is about 3 times better connected at 89%. It fits in at the bottom right of the table. We'll now fill in intermediate hybrid network architectures along with their connectivities. Another way to represent the same information is to plot connectivity versus percentage of random edges, as shown in this chart. This line represents the local connectivity of 30%, while this line represents the random connectivity of 89%. As we gradually change edges from local to random, we expect that the connectivity of the resulting hybrid networks will improve. The crucial question is, how fast? The simplest guess is a linear relationship like this. A more pessimistic guess would be a sublinear relationship, where most of the edges must be changed to random before we see a significant connectivity improvement. A more optimistic guess would be a superlinear relationship like this, where hybrid network connectivity quickly improves with just a few random edges. In this case, we can design a hybrid network retaining most of the local structure of the original local network, but with a connectivity closer to that of the corresponding random network. These are the naive possibilities. More specifically, we could try to guess the connectivity of a particular hybrid network, for example, one with 20% random edges. A pessimistic guess for this network might be 35% connectivity, while a simple linear guess might be 40%, and an optimistic guess might be 50%. Let's test this. Here's our 20% random hybrid network. What is its connectivity? This is the moment of infinite suspense. Perhaps surprisingly, the answer is 78%. This number is much higher than any of our naive guesses. We add this network to our table and our connectivity plot, along with an approximation of the connectivity curve between 0 and 20%. This curve is so steep that it suggests a completely unexpected possibility. Perhaps the hybrid connectivity actually exceeds the random connectivity at some point between 20% and 100% random edges. Well, let's see. Next, we examine the case of 40% random edges. This network is still mostly local and retains substantial local feature recognition capabilities. Its connectivity, however, is 91%, exceeding the random connectivity. We fill in this network on our chart and update our hybrid connectivity curve. For completeness, we fill in the cases of 60% and 80% random edges, both of which give even higher connectivities. We now complete the hybrid connectivity curve. We can now make a distinction between hybrid configurations with lower connectivity than the random configuration, called hybrid disadvantage, and configurations with higher connectivity called hybrid advantage. Hybrid advantage is a surprising and fortunate mathematical phenomenon that allows us to have our cake and eat it too, achieving a hybrid network with architecture that is comprehensively superior to its simpler ingredients. 3 of our 4 hybrid networks here exhibit hybrid advantage. Of course, the networks in our example are unrealistically small for most real data problems. Does hybrid advantage also occur for larger networks? Well, fortunately, hybrid advantage actually increases for large networks, so that hybrid networks with just a small percentage of random edges can be much better connected than corresponding local or random networks. Now, a complementary viewpoint on hybrid advantage is to track how many edges are required to achieve a fixed target connectivity, say 99%. From this perspective, the challenge is to create an efficient network that will train rapidly, since training time is largely determined by number of edges. Using a specific moderately sized network design as an example here, the number of edges required drops precipitously from the local requirement to a hybrid minimum, then rises back to the random requirement. This illustrates how hybrid architectures can accomplish the same tasks with much more efficient networks. The potential advantages of novel hybrid network architectures are striking, but my description here necessarily compresses certain details and raises questions and possible objections. The rest of this video is devoted to answering a few of these. One possible objection is that it is easy to achieve 100% connectivity using architectures I didn't mention. For example, here is a very sparse network that's 100% connected. Now, nobody will take this specific network seriously, but there are many less ridiculous instances of 100% connected networks. For example, it's common to use dense final layers in convolutional neural networks to compensate for poorly connected early layers. There are also special network types that precisely match families of nodes with connecting edges so that everything is completely connected in a minimal fashion. An example of this in the literature is so-called radix nets, which work by combining numerical bases of different sizes in a clever way. There's also a general class of so-called expander graphs, which are a type of network that exhibit rapid horizon growth as one moves away from any node. Random networks fall into this category. It's actually true that for a random network, the size of the horizon or perceptive field will grow approximately exponentially as you move away from a given node. So there's this broad theory of connectivity that must be considered if one's going to take the problem seriously. Now, I've designed other highly connected network types myself using multiply connected manifolds, orbifolds, and other mathematical methods. I've also utilized partially random structures that exhibit good expansive properties while guaranteeing the existence of certain connections. Finally, I've explored methods of slightly modifying an existing network to obtain a network that retains the same good properties while achieving 100% connectivity. After all this, it's natural to wonder if the network connectivity problem as I presented it is real or fictitious. The answer is that the novel hybrid network architectures I've been showing you are much more robustly connected than most of the architectures I just mentioned. Cheap connectivity is computationally ineffective. What we really need is many complementary reinforcing paths between typical input-output pairs. The totality of such paths is called the computational interval between the two nodes. It plays the same role as an Alexandrov neighborhood in relativity or causal set theory. It's called an interval because it consists of all the structure between the input node and the output node. Now, this diagram shows a robust computational interval between two vertically aligned nodes in a totally local network. I will animate the picture to show the many reinforcing paths between the two nodes, which allow effective data transmission and sorting. The problem with this network, of course, is that it is poorly connected overall because it's too local. For nodes that are not vertically aligned in this network, the computational interval drastically shrinks and then disappears. Going back to our bottleneck network, each computational interval consists of a single path, which is practically useless computationally. Now, this diagram shows the computational interval between vertically aligned nodes in a novel hybrid network. I will animate the picture to show it more clearly. The black edges represent the part of the computational interval coming directly from the kernel architecture, while the lighter magenta edges show the diffuse cloud of other paths in the interval. Overall, the interval is larger and more complex than the interval in the corresponding local network, even though the total number of edges in the two networks is the same. But the hybrid network begins to show a really decisive advantage when we shift to input-output pairs that are not vertically aligned. While the contribution of the kernel architecture shrinks and disappears, as in the local case, a robust diffuse structure remains due to the non-local connections, and this also engages remote parts of the kernel architecture. Finally, this diagram shows a computational interval in a totally random network, which is large and complex but disorganized. For some types of data, the high connectivity of this network is enough to make it computationally effective. But hybrid advantage implies that appropriately designed hybrid networks can exhibit even greater connectivity while retaining substantial organization in their computational intervals. Now, a second possible objection to the use of hybrid network design is that the whole connectivity viewpoint that I've talked about focuses attention on networks with many outputs, which is just a special case. This is because networks with few outputs tend to funnel information in such a way that high connectivity is almost automatic. For example, the totally local network shown here, which is similar to the breast cancer networks I demonstrated earlier, is 86% connected despite having rather sparse structure. This is because the layer size is decreased by factors of 2 from 32 inputs to just 2 outputs. Meanwhile, using a uniform layer size of 32 with the same kernel architecture, we get a network with just 26% connectivity. From these examples, one might worry that hybrid advantage applies only to the naive case of uniform layer sizes. Since layer tapering is so common in practice, this might limit the applicability of hybrid architectures. There are at least 2 possible responses to this objection. First, many of the machine learning problems of greatest interest today do in fact require networks with many outputs. One general problem of this type is the identification of individuals among a large population. In this case, the inputs are identifying data such as images, genetic information, or maybe transactional information. Such data might involve tens or hundreds of thousands of inputs, but the number of outputs might be even larger because it's the total population size. A second general problem of this type is identifying precise locations on a large and complex structure. Such problems arise in genetics, for example. A third such type of problem occurs when we ask a network to generate some complex data, for example by asking it to generate an image from a verbal description, as in a police sketch. Besides being important, problems like this require networks with many millions of edges that take significant time and resources to train. This calls for the sparsest architectures possible, making hybrid advantage particularly attractive. A second response to this objection is that we might need better connectivity in just a portion of a network. Many, perhaps even most, networks have roughly uniform sizes in their first few layers, and we might need information to percolate more rapidly through these early layers. For example, here's a schematic diagram of a simple CNN, convolutional neural network, for recognition of handwritten digits. Overall, the network tapers drastically from 784 inputs, which are pixels in 28 by 28 images, to just 10 outputs, which are the 10 digits from 0 to 9. Such tapering makes high connectivity easy, and this particular network guarantees 100% connectivity by using a dense final layer. However, if we isolate the first 4 layers of the network, then the resulting subnetwork is just 7% connected. The problem with this situation is that the network must very quickly assemble and analyze a lot of disconnected local information in just 3 additional layers. It might be better to allow for greater information transfer in the earlier layers by adding some hybrid structure. A third possible objection to the use of hybrid networks is that even modest non-local structure might disrupt local information processing in networks such as CNNs, convolutional neural networks, that use weight-sharing schemes. This is essentially a symmetry breaking issue. Convolutional kernels filter different spatial regions uniformly to detect and assemble local features, and sporadic additional connections with free weights might interfere with this process. Here is a familiar schematic description of feature assembly in an image recognition CNN. The input layer detects only simple local shapes. Subsequent layers progressively detect combinations of these simple shapes, which can eventually be recognized as objects with semantic meaning, such as digits. Any structure interfering with this process might be counterproductive. Before discussing if this actually happens, I want to point out that restricting analysis to local regions can unnaturally limit results, even for data types on which CNNs have shown the best success. For example, photos routinely exhibit non-local composite features, such as pairs of ears and eyes, whose components are spatially separated. Due to slow growth of perceptive fields in a local network, standard CNN feature assembly can detect such composite features only many layers after detecting their components. Besides wasting opportunity, this introduces the risk that the network will try to assemble such components locally in some spurious way. Another domain with both local and non-local attributes is game strategy, which extends to real-world applications through virtual reality and other modeling scenarios. Here I use the familiar example of chess. This is a mid-game scenario between two grandmasters. While some of the pieces, particularly the pawns and kings, exert purely local influence, we also see many instances of action at a distance. For example, the bishop supports the pawn along the diagonal, the rook threatens the pawn across the board, and the knight's influence is completely non-local. The queen's influence covers more than a quarter of the board in this case. Now, chess remains local enough overall to yield to CNN-type methods, which were validated spectacularly by Google DeepMind's CNN-based engine AlphaZero about 5 years ago. Since then, DeepMind has turned to applications such as protein folding, but computer chess has continued to evolve with back-and-forth battles between open-source engines Stockfish and Leela Chess Zero. Most of the strongest chess engines today use CNNs in some way, but much of the low-hanging fruit in this area has already been harvested. Due to the significant non-local aspects of chess, I wonder if it might be time for a chess engine based on hybrid networks. A second answer to the objection that non-local structure can interfere with weight-sharing schemes is that I've tested it and it doesn't seem to happen, at least for small examples, if the networks are designed in a reasonable way. I have no reason to expect anything different for larger networks. In particular, I've combined local kernel architectures that have the same type of weight sharing and cross-correlation used in convolutional neural networks with sparse random structure and have obtained results as good or better than in the pure convolutional case. Below is a schematic illustration of such a network, restricted to just 2 dimensions so that the layer-dependent structural changes in the network are visually evident. In this case, the network begins with almost completely local structure in the first layer or two, then adds increasing non-local structure moving toward the output layer. This approach seems to work well for data such as images, which are mostly local at the smallest scales. For such data, the goal is to convert the local geometry of image microfeatures into semantic information about the qualitative meaning of the image. The goal is the same as for CNN, but the approach allows non-local composite features to be assembled faster and achieves much greater connectivity, eliminating the need for costly dense layers near the output layer of the network. Despite being small and two-dimensional, this image looks messy because it shows the entire network. The kind of structure involved can perhaps be better understood by returning to the viewpoint of a single output neuron. This also allows us to change and look at a more complicated three-dimensional network. The completely local structure in the first layer means that the patches of the perceptive field of this output neuron in the input layer are always at least as large as a single kernel. Here I animate the image to show the structure more clearly. Now, there are many other possible questions or objections about this whole technology that could be examined, but the few I've covered here should at least illustrate that many of the main issues have been considered and tested. The real test, of course, is the performance of hybrid networks on real data sets, and that is the principal subject of the next few videos. Thank you so much for watching. In the next video, I will show you the details of how I would process your favorite data set, using the familiar breast cancer data set as a toy example. I will explain how data pre-processing works, show a variety of different network construction algorithms, and demonstrate how to obtain and interpret results. Subsequent videos will expand on these methods using larger and more complicated data sets.